Okay, welcome to this latest of the winter series of talks from the Moby Centre here in Cambridge. I'm very pleased to welcome today Professor René Mayrhofer, who's going to tell us a little about the Android platform security model. René, until 2019, was Director of Platform Security for Android at Google, and is today here speaking with his university hat on. Over to you, René.
Thanks, Alistair. I had actually been looking quite forward to visiting you in Cambridge again. Unfortunately, we have to do it this way. I think most of us are getting slightly sick of the nth Zoom meeting every day. I'm still trying to make the best of it to have this chance to speak to all of you, which I'm actually quite delighted about. Nevertheless, if the current pandemic moves past us, I'm always too optimistic, then I hope that we can continue some of that conversation, maybe face-to-face later on, either in Cambridge or in Linz. Alistair, please already feel invited to come and visit us over here as soon as we can manage that again.
Likewise, thank you.
Thanks for the introduction. As Alistair already mentioned, I am already still involved with Google in a bit like an advisory role for specifically Android platform security, but today I'm explicitly not speaking for Google, but only speaking in my academic role for Johannes Kepler University Linz. Before going a bit more into Android security itself and what we think of as the platform model, I would like to start with some of the context. Why are we actually talking about mobile security? I think mainly because we are seeing a strong convergence of many services that are indeed quite security critical into our mobile phones. Not only payments, which are in many of our countries already part of the daily business, or even keys, opening, closing doors, unlocking, starting cars with our mobile phones, but also increasingly having access to critical services, medical services, managing the production floors of some factories, or even directly managing parameters and control of industrial critical systems like our power grids from our daily standard off-the-shelf modern mobile phones. Slightly farther ahead, but not too far into the future, we're also seeing our identity documents, our country state provisioned identity documents from driving licenses up until passports already being discussed and in some cases already moving into our smartphones. So the question of how to secure all those critical use cases is already pressing and is becoming more so as we move on with more of these scenarios. A second piece of context is that the Android ecosystem is massive. I don't think we need to discuss the specific numbers, but there are thousands of brands, tens of thousands of different devices running Android, millions of apps and billions of users somehow using the Android ecosystem. And with those numbers, I only mean those devices that are actually allowed to call themselves Android, and I'll come back to what that means. There are other devices, like for example, the Amazon Echo devices that use the Android open source project's code base, the AOSP code base, under the hood without supporting the installation of arbitrary Android apps and not calling themselves Android. And I'm certain there are others out there, maybe not as massive in deployment as the Echo devices, but there are many other device categories that use the very same underlying code base. And if I talk about the Android platform, I implicitly mean all of those devices and what we can do to make them slightly more secure. If we look at how a device comes to life, then we have different stakeholders, which also is part of the complexity of the ecosystem. We have the chipset manufacturers, we have OEMs, the original equipment manufacturers that assemble multiple chips to actually make devices. And those devices are used by actual end users who, that is the definition of a smartphone, install third-party apps by app developers. And somewhere to the side of that picture, we have the operating system vendor. Unfortunately, those interactions between those stakeholders are already a little bit more complex even on the abstract level. because the chipset manufacturer itself doesn't really exist in that form. What we have is a chipset designer who might take some IP, maybe from ARM or other companies that make the actual core design, and molds that into design that can be made into an actual chip. But the same company typically doesn't actually make those chips. This is handled by fabs that actually produce the silicon. Those fabs produce silicon for multiple different chipset designers and also produce multiple categories of those chips that are then assembled not directly by the OEM, but what we call an ODM, an original device manufacturer, who typically produces the electronics designs of combining multiple chips together and already interacts with the operating system vendor to make the firmware, the driver support happen. So the operating system is taken by the ODM combined with potentially even third-party libraries for additional chips like fingerprint readers and others that the ODM might not make themselves, and making a whole system out of that. This system is then taken by an OEM, and that is often the first company name that actually appears to end users. Those are the Samsungs, Huawei's, Apples, etc. of this world, who actually make boxes with devices in them and put their name on the boxes. But there's a huge chain before those companies even get involved. Of course, some of those companies like Samsung are big enough that they have multiple roles. They are a chipset designer, a fab, an ODM, and an OEM at the same time, but also tend to combine with chips from other manufacturers and fabs. Those third-party services offer additional value sometimes that is added to the operating system itself. And on the other hand, those third-party services are also what is responsible for shipping the boxes with the names of the OEM on the outside to actual shops and maybe directly to end users, because there are logistics services involved. We somehow need to move those physical boxes around. And as mentioned, the shops are the ones where you can go physically if you're not in a lockdown and actually buy the box. And any one of those stakeholders in that long chain could potentially be explicitly malicious, could insert code that includes backdoors, could maybe just insert code that is not intentionally breaking the confidentiality or the integrity of a device, but that just adds some spider. I mean, ODMs and OEMs have been known to have received a bonus for including some adware from third parties to get a few dollars for each box that they ship by pre-installing this particular application. And I'm not putting names on there, but big social networks apps have been known to actually also pay OEMs to include their app in the pre-installed firmware. And that includes also shops. We know that from certain regions, from certain markets, shop owners who sometimes provide a value-add service by helping users to initially set up their device, not only set up their device and help users create the Google and Apple accounts, but also install some apps that they make a cut off of shipping to their customers. So in this long chain, how do we actually manage to keep that whole ecosystem somehow in a state that approaches what we would call security? Now, of course, when we're talking about security, it's no good talking about technical measures from the start. We always have to ask the right questions first. And that means, what do we actually want to protect? And what we want to protect is, I think, classified into three categories when we talk about mobile devices like Android phones. First, of course, we want to protect user data. That is the data that is stored on devices themselves, that belongs to users, and that often paints a very close picture about their personal, their private lives. There we can, of course, apply standard methods like device encryption, user authentication, and usual operating system mechanisms like memory and process isolation. An upcoming, from my point of view, quite interesting topic is what we do with personalized machine learning that happens on device. So from a privacy point of view, it's obviously positive if machine learning, if adaptation to users' behavior happens on their own device, not in some cloud instance. However, those models that are trained and used on device effectively become an oracle for user behavior, because they are trained implicitly with user data, with user input, with user behavior. And because in the future, we are moving much more towards having those models trained on the user device. We are slowly getting the computational power to train deep learning models, or at least adapt deep learning models on user devices, which means that I predict we will see lots more of those uses of personalized ML on device. Because data is not shipped off device, it becomes much more tempting to use all the data that you can from the device for training, because seemingly there's no privacy problem. But if those models leak, if those models can be extracted, or if another malicious app on the same device can query those models, they can be abused as oracles. Maybe not to directly reverse engineer the raw data that went into it, but we've seen that ML deep learning models can be quite effectively used as leaks for the data that was put into their training. Second, device integrity should be protected. Of course, that's the usual thing. We don't want malicious parties to be able to undetectedly tamper with our devices. But I think the interesting question there is against whom? Should the device integrity protect against the legitimate owner, against the user of the device, to guarantee DRM, to guarantee that a streaming service cannot easily be copied and so on? Do we want to integrity protect against even the ODM, against even the OEM? Should the OEM itself be incapable of tampering with the device before or after it has been sold? There are really interesting questions of who is actually in our threat model of being potentially able to tamper with our devices. And of course, to have an ecosystem be successful, we need app developers also to get some guarantees, and that includes protecting content and generally IP of developers and their streaming services. The Android platform security model therefore has some, I think, rather obvious threats that we can combine into a threat model. Of course, we have the assumption of physical access. By definition, mobile devices are sometimes under control of adversaries. During a border control check, just leaving them live around in the office or at home and so on, we have to assume that adversaries will be able to get physical control over our devices. And since we connect to roaming networks, to wireless networks, we of course assume the standard passive eavesdropping and man in the middle or on-path attacks on the network. So far, that is not very surprising because these are standard threat models that we've been using for ages, specifically for mobile devices. But for smartphones, by definition, we have some additional threats. The first one being that the intrinsic definition of a smartphone is that you can install third-party apps. So of course, we have to assume untrusted code being executed on the device, being able to abuse any APIs, and potentially including misdirection on the UI layer, trying to misinform, deceive users through their UI, maybe even faking the UI of other apps. And untrusted content in the sense of complex media formats, etc., being processed by the device, including just the reception of an MMS message and others that have been seen to cause security issues in the past. I think even more importantly, the new threats that we have to consider is that insiders in, remember that long chain that I showed a few slides back, anywhere in that chain, there might be insiders in any of those organizations that can get access to the signing keys and therefore can potentially undetectedly tamper with code running on the device or inject new code or sign third-party apps with the signing keys off the platform, signing keys for that OEM vendor and so on. And yes, that very much includes our crypto X.0 backdoor debates that we're currently having on the EU level. That maybe there will be legally mandated backdooring and access to signing keys of players in that long chain of stakeholders. I think a security model for such devices at this time needs to explicitly include insiders as such a threat. Now, how does Android approach that? There are 5 basic rules that the platform security model is based upon. The first one is a multi-party consent. Normally 3 parties where the app developer, the platform, and most importantly, the user need to consent before an action can happen. If any of those parties do not consent, the action by default will just be denied. Depending on the scenario, there can be less, maybe sometimes only 2 parties, like the platform and the user, if there's no third-party app involved, or maybe 4 parties, if, for example, you have an MDM a mobile device management with an enterprise policy involved that can also add additional restrictions to actions. Then we assume that the whole ecosystem is an open ecosystem. There's no single point where apps need to be vetted, where users or platforms need to be vetted, but anybody can make Android devices and can make Android apps. And there's no single gatekeeper in there. For that to work, we need rule number 3, meaning that the security requirements that we have on the ecosystem are actually a part of the compatibility requirement. Any device that calls itself Android needs to fulfill all the security requirements to be able to participate in the ecosystem. Then something that is really to do with those devices being directly end user accessible is that a factory reset should restore the device to a safe state, which is different to the standard operating systems that we have on our laptops, where even if you just delete user data, you might still have a tampered with system. Android tries hard to have that simple user interaction of initiating a factory reset to restore the device into a state where there is an extremely low probability of malicious software still being installed. And that applications and not users are security principles, meaning that applications cannot, a single application installed by a user cannot act with the full privileges of that user, which is also in contrast to most current desktop and laptop operating systems. Here, applications stand for themselves and are in their own sandbox and do not, so to speak with the voice of the user. And that makes ransomware and other such Trojans mainly a non-existent thing on the Android platform, because an app simply is not capable of accessing the content of all the other apps, the data that's stored by all other apps. Now, this is a bit lofty, it's a bit abstract. How do we actually implement this in engineering terms? The main goal of security methods is typically isolation, or you could also say the main means of achieving security goals is by isolation, by giving components only that amount of control that they really need. And so let's look at how Android separates different components. First, as mentioned, applications are security principles, so applications are separated from each other and by default cannot access each other's content or internal methods. They are in their own sandbox and there need to be explicit interfaces for applications to interact with each other. On Android, for quite a number of versions, we've also had something called the work profile, where one set of apps is supposed to be in the personal profile, that's the private life, and another set of apps, or maybe even an app that is used in both sides, but is in a different instance, a different instantiation, is within the work profile. And that work profile can be turned on, can be turned off. There can be sharing of data, explicitly enabled sharing of data between apps in the work profile, but by default, they are separated from the personal profile. So you can separate the two heads that many of us wear on our single devices more effectively. I still believe work profiles are one of the most underappreciated and underused isolation features of Android devices. And I've been trying to advocate more for them for the last 2 years to not only use in enterprise context. For example, for my wife and daughter, for their various, sometimes slightly weird school apps that they're forced to use. For my wife from the teacher's point of view, for my daughter from the pupil's point of view, I actually enabled work profile on their devices to keep those off and also enabled to turn that off and have, if they really need to use WhatsApp or others, force them not to have access to the full family phone book and so on. So I think work profiles are one additional layer of separation that is really maybe not unique in Android. There are other desktop operating systems like QxOS who have something similar, but on a widely deployed operating system is a concept that is not used enough in practice. But there's more. We can also have multiple users. So this is really for shared devices. When you have a family tablet where it's not only one physical user using the device wearing multiple hats, but actually different people, different individuals using the same device, which are just additional Android users who have their own sets of apps, or maybe the same set of apps, but different instantiations, different data partitions for those apps that are completely separated from the other users. So this is back to standard Unix land multi-user concepts that we've had for decades. Those partitions are enforced by the Android Linux kernel. And that also enforces an isolation of the system services. System services that control, for example, the networking stack, but also through hardware abstraction layers, the interfaces to hardware drivers. And those have actually traditionally, not only for Android, but for most operating systems, been a source of the gravest security issues. So partitioning those off into separate processes, into separate sandboxes, has been a huge win for security. Why are those drivers and HALs typically so bad from a security point of view? Because they're close to hardware, and so often written in C and C++. And those of us who are into security know what that means typically for the security of such a component. So those are tightly sandboxed neural nets. But there's more, or as people would say, there's turtles all the way down. We have on modern devices a hypervisor. So we have virtual machines there where Android and everything from the Android Linux kernel and above is really just one virtual machine, and we have others next to it that at the moment are mostly used for OEM specific services, but in the future will probably be more used for the dedicated on-device machine learning that I mentioned. I suspect that many of those approaches will run in separate virtual machines to give them slightly better isolation from the main operating system, and maybe even closer access to some hardware accelerators like those TPUs and other neural network processing units that are on CPUs. There's another turtle there, because next to the hypervisor layer, at least on ARM architectures, we also have a hardware mode monitor switching between two hardware-assisted security modes. In ARM terminology, that's a trust zone. And this is where on the right side, we have a trusted execution environment, which is strictly separated from all that is Android and includes services like, for example, Gatekeeper that does the on-screen lock screen verification, the PIN code, password, pattern verification, has Keymaster for storing keys, or fingerprint matchers. So biometric authentication, biometric matchers live in this trusted execution environment. But it's not only that. OEM-specific extensions go in there as well. That includes DRM, that includes many other things that the OEM might add. And to be quite honest, this right side here still scares me a little bit, because for a trusted execution environment, the complexity that we have in current Android devices is far too high. In the next few years, we should pick some of those components out and put them, for example, into VMs or into standard processes on the Android side, and not have them into such a highly privileged layer that can normally easily break the security guarantees of the Android Linux kernel if we have any compromise on the TE side. And in the last few years, we have, of course, seen compromises here for this trusted world, for this TE side. One question you could now ask is, if we have that work profile separation, which I'm such a fan of, should the work profile, something that the enterprise controls, be able to change parameters for the personal side? Should that work profile demand that my lock screen for my whole device has at least 8 characters and has some mixing of upper, lowercase, etc. in there? Should the work profile be able to disable installation of third-party apps on my personal profile and so on? And that's one of the hard questions that often come up as trade-offs in those layered designs. Do we allow that or not? And I don't have a clear answer. I can happily argue both sides of this coin for an hour each, and I still can't tell you which of those parameters are ideally controlled by a work profile for the whole device and which not. If there's interest in this, I'm happy to rant and deep dive into many of those simple parameters, but it's just one example of isolation provides trade-offs, and we need to solve those trade-offs at some point. Now we move beyond the main CPU, and I'll leave it with that because there are many other CPUs, many other processors on a modern platform, from the radios through a GPU and other sensors, ML accelerators, up until the temper-assistant hardware, which is basically smart cards embedded into our mobile phones. And those all talk to the main CPU, but are still additional layers of isolation, where if you have something that Android calls strong box, then the key master that we see here on the TE side on the main CPU can be enriched by storing certain keys, certain cryptographic keys in the smart card component, which is even outside the main CPU, and therefore hopefully on a microcontroller with less complexity than the main CPU. Now, that Android security architecture, that isolation, builds mostly on the application sandbox that Android apps are subject to. All applications on Android must be signed so that they can be installed. While there is no central gatekeeper, no central signing instance that needs to sign developer certificates or applications, those developer self-signed signatures at least provide non-repudiability and automated updates. Otherwise, besides this signing requirement, which can be self-signing, there is no other requirement for applications really. Users can install, or can write and install arbitrary applications, and apps can be written in any language that can be compiled to execute on the target platform. And this open ecosystem requirement makes it really hard to have a sandbox on multiple layers. So how does that work? When an Android app is installed, it just uses standard Unix principles of assigning a UID. Android interprets this UID not as a user ID, but as an app ID. So upon installation, an app will be outfitted with a dynamically created UID, and this forms the basis for a sandbox. The app by default can only access resources that belong to this UID, and these are private data files that the application stores and not much else. This is enforced by standard file system DACs, but as with newer Android releases, starting with Android 4.4, also with a mandatory access control policy, SE Linux in the kernel, which is quite extensive. And that includes even the debugging and shell users on devices themselves, which are not root by default, but are limited to a special such Android UID, the shell UID, and also limited in what they can do. Now, there are two layers, mainly two layers on which this sandbox is enforced. The first is the file system DAC, which is based on those UIDs, those Android IDs that are assigned upon installation. And they are enforced in an interplay between standard DAC and MAC policies. But there is a second layer on top, which is permissions on Android services. And this is enforced on the framework layer. So whenever an application calls an API that the Android operating system offers, that is a well-supported documented API, then by crossing the boundary from one process into another, into an operating system process, this requires a permission typically to be granted to the application. And those permissions can be checked on a very fine-grained level by the frameworks themselves. And there we have, I would say, semantically a change from the access control list type of system that we have on a file system to a more capability-based system that we have enforced on the layer of APIs, on those permissions on those API calls. There is another layer of additional security safeguards and isolation mechanisms, like, for example, the Linux kernel capabilities that the kernel can enforce for applications, and SECOM filters, but those are not widely used throughout the system, but more for specific applications. For example, the Google Chrome browser is one of the heaviest users of SECOM to isolate its own processes within the app to make sure that, for example, a JavaScript renderer and so on is as tightly sandboxed with regards to a Linux syscontrol attack surface as possible. Now, if applications want to cross that sandbox, want to cross that boundary, they need permissions. And the permission checks and the crossing of one's sandbox to another is implemented mostly by Binder, which is an addition to the Linux kernel. That is really an object-oriented inter-process call interface. And that is typically, so for the last few years, this hasn't been a source of security issues, but because this is such a basic component of Android sandboxing, of Android inter-process communication, it means that any bugs in this binder code will probably lead to a compromise of most of the system. This is where, as an attacker, I would start looking, although attackers have looked long and hard at Binder, and now I think most of the low-hanging fruits have already been picked, and I don't expect completely new issues to turn up quickly. I already said that Android applications need to be signed. This is not only true for third-party applications, so not only something that is installed from the Play Store or other app stores, but even the system apps themselves have to be signed. And again, turtles all the way down, not just the system apps, but also the system images themselves, the boot image, the recovery image, the system image itself, the vendor and product images, and the various different partitions that we have on an Android device all need to be code signed for the bootloader, as long as the bootloader is locked, to execute those components. And this is really a chain of trusted forms where the bootloader itself is signed with an OEM key that needs the chipset vendor's private key to actually sign. That checks a public key that's embedded in the bootloader. That's typically for the OEM's version of the system image. In the system image, we have embedded public keys to check the system apps and so on and so on. It's a chain of trust. Many devices support unlocking the bootloader. At least on the Android side, the default is that a device can be unlocked. Sometimes that means losing functionality. Samsung, Sony devices, for example, blow some eFuses or remove some crypto keys pre-installed on a device when the bootloader is first unlocked. And that might mean that you permanently lose some access to hardware functionality on that device. Other devices like the Google Pixel line, you can at will lock and unlock the bootloader, and if you lock it again, you restore full device functionality. Now with an unlocked bootloader, arbitrary non-signed system images can be installed. That is good for development, that is good for customizing devices, that is good for taking control over one's physical device. But from an app point of view, security guarantees go down. So should we give apps access to that unlocked state of the bootloader or not? Should we tell apps if it has been unlocked or not? Again, I can argue both sides, and this is one of the other trade-offs that we have to take with the Android platform security model. At the moment, the answer is if you take what's called keymaster attestation, you can actually learn if the bootloader of the device has been unlocked. And if it's still locked, what's the top level hash of the running firmware is. So this is some form of remote attestation, but not as advanced as the TPM's direct anonymous attestation. It's not a DAA protocol. How do we deal with the whole complexity? Typically, at the moment, at least within the Android ecosystem, on two sides. One, there's the standard side where the Android compatibility definition document, the CDD, specifies a long list of requirements devices that want to call themselves Android have to fulfill. And then there's the other side of enforcement. There are compatibility test suites and vendor test suites, security test suites, and so on, that try to verify as many of those standards requirements as possible in an automated way. And those together try to check if a custom Android firmware created by any OEM fulfills the basic security requirements and other functionality requirements to be able to call itself Android. And only, let's say, for SE Linux itself, which is one of the biggest tools for enforcing the platform security model, there are over 800 tests in the current CTS, STS, and VTS suites that check only that those SE Linux rules, the SE Linux policies are correct or are in an expected state. The CDD rules are also used to push the ecosystem further, to from one version to the next, actually increase the security stance. And one example for that is encryption of on-device encryption. Android 5 introduced a long while ago what was called full device encryption, a block level based encryption layer underneath the actual logical file system that had some usability issues. For example, for multi-user access, you first, after reboot, had to enter that only one single password to derive the decryption key for the whole device before those multiple users could actually log in, which meant that reboots were hard on shared devices. Android 7 introduced file-based encryption, which pushes the encryption to the logical file system layer and allows files to be encrypted with unique encryption keys. At the moment, this is used, for example, to have a separate encryption key, of course, for every user, but also separate encryption keys for the work profile as distinguished from the personal profile. And through CDD rules, through the standards and specifications, Android 9 added the concept of metadata encryption to also encrypt file names and other metadata. Android 10 made FBE, file-based encryption, mandatory for all new devices. For all devices shipping with Android 10 and onwards, they have to be encrypted by default. And this took a long time. This took like 5 years in the ecosystem to make it happen, because the Android ecosystem is so diverse. There are not only the flagship devices with 1,000 euros, pounds, dollars, and so on, which have capable CPUs with hardware accelerated encryption engines. There are those $50, euros, pounds devices as well out there who have CPU generations that are probably 7, 8 years old, and they don't have those AES silicon cores. So with Android 10, we actually introduced a software-based encryption layer, which is based on SHA-20 and can execute even on those low-end CPUs with reasonable overhead, something that is not noticeable in normal use, which made it possible for the first time to actually enforce that. And yes, this is something that, because it took so long, we are slightly proud of having to actually manage. That if anybody of those billions of users buys any device that ships originally with Android 10, they can be guaranteed that data on their device will be encrypted properly. But encryption is only one side of the coin, because the lock screen on Android devices, that enables access to the encrypted data. Once you have a device already booted and the encryption key has been derived once, it lives on in memory, and only the lock screen determines if data can be accessed or not. That lock screen is typically a mostly binary distinction. The device is either locked or unlocked. If it's locked, you can't do much. You can maybe make an emergency call and you can see some notifications of incoming messages on the lock screen, but that's pretty much it. Oh yeah, and you can take pictures, because people do that a lot. Now, if it's unlocked, you can do everything. There's no further restriction on an unlocked device normally. I mean, yes, caveats, there's the work profile, there's device app pinning and so on, but normally this is really a binary distinction. This is why it's so hard to find a compromise that is both secure and usable for the hundreds of times that we pick up our phone a day and unlock them to check. And so Android has what's called a tiered authentication model, with the primary authentication being knowledge factor based. That's a PIN code password pattern that is always required and is always used to also derive, for example, the device encryption keys. Then there's secondary authentication, typically biometric, which is not assumed to be as secure as the primary one, but is more usable and is somewhat constrained. For example, every 72 hours, you have to fall back to primary authentication. And then there's tertiary authentication, for example, having a Bluetooth device like your smartwatch or your car, hands-free, set in range and so on, that will keep the device unlocked. But this is assumed to be the least secure and is most constraining. For example, every 4 hours, we'll have to fall back to either secondary or primary authentication. Moving slightly onwards for the last few minutes from just the lock screen to authentication a little bit more in general. What is an Android device and what do we use it for when it comes to digital authentication, digital identity? As individuals, we not only authenticate to services, we open doors physically, as mentioned, we pay, we travel, and so on. And those real world actions that we do are more and more verified electronically and supported by our mobile phones. We see the mobile driving licenses, we see our transport tickets, and so on, all move into mobile devices. How do we do that? Let's take the example of a mobile driving license. There, typically, when you use your physical, your plastic cards, your paper driving license to just maybe in a traffic check, you hand over that document and it lists all the attributes that you have, your name, date of birth, your face picture, sometimes depending on the region, the place of residence, biometric features, some vehicle classes that you are allowed to drive, the restrictions like having to wear glasses and so on. That all should work offline, but we can more or less easily just copy that over to a digital version of transmitting that through NFC, through QR code, through BLE, and so on. However, the driving license, to stick with that example, is used for so much more, because that's one document that most adults have with them. It's also very often used for age verification. Now, for age verification, transmitting all those attributes is far too much. It reveals far too much of one's identity. With the plastic card, we can't do better. If you show the plastic card to a shop owner, to a clerk, to a bouncer, and so on, you automatically transmit all your personal data, all your identity attributes. While what you actually need is really just a face picture to make sure that, yeah, this is my driving license and the age. You don't even have to have the full date of birth there. It's just, am I over 18 or not? Am I over 21 or not? That should be enough. It's maybe even more drastic if we look at location-based services. So for example, public transport. To pay for public transport, you could just record your whole location history and pay for whatever pieces or whatever parts of the public transport network you travel. But those location traces are highly sensitive. From location traces, even without coupling them to name, you can tell where people live and work. You can probably tell their religious beliefs, their illnesses, their hobbies, and any particular preferences just based on their daily physical travel. While for public transport, the only things we really need are the place of entry and exit into that system, or from a privacy perspective, even better, just proving possession of a time-based ticket, that I have a valid monthly or yearly or daily pass and nothing else. And our digital versions of licenses, of tickets that we store on our mobile devices should support that, should support only transmitting as much data as we really need. To pick another example, because we are in the pandemic, if you do contact tracing, the same applies. You could, of course, try to do the full location history, but that's far too revealing. The only thing you need is that there was a contact with a pseudonymous person X for Y minutes and days. And this is luckily exactly what the current APIs, the current exposure notification APIs on our mobile phones do. This is all they transmit and not more. Now, we are involved with the ongoing ISO standardization 18013-5, which is the upcoming mobile driving licenses. And I won't go through all those requirements, security and privacy requirements that we managed to put into the standard, but my slides will be available for reference later on. I would like to still ask one question, though, again, pointing out that we have some trade-offs to decide. Should either the phone, the holder device, or the reader device, the other device that reads my attributes, be required to run on strictly certified hardware and software? We could offer better security requirements if yes, but it would also lock the ecosystem down more and make it harder to actually use those digital licenses, those digital attributes on maybe an open ecosystem of potential readers, of potential users. So maybe we only certify a little bit, which is the smart card in the holder device, maybe even just a small smart card in the reader device. Well, we don't certify readers at all. We only certify the holder side with an embedded smart card. So this is an ongoing discussion that is currently happening. Android 11 has actually managed to take some of our concepts from 2016, 2017, from the ugly research prototypes on the left, and transform it into a framework that allows nearly arbitrary digital licenses to be stored on Android devices. This is already included in Android 11, and we expect first mobile driving licenses by certain states and countries to be starting to be issued sometime next year based on that ISO standard that is now supported with Android 11. Finally, this was abstract in the model and in the isolation and engineering type of sense of what AOSP can do. But how can we actually tell if specific devices, those that we hold in our hands, conform to those security requirements, or how well they do on certain of the trade-offs that are maybe not hard requirements and cannot be checked automatically by CTS, VTS, and so on. The goal of a project that together we do with Alistair and other colleagues at Cambridge, so this is a collaboration project between Cambridge and University in Linz. We're trying to give meaningful data to users and organizations to allow them to make informed decisions of security of particular devices or particular OEMs. And we try to do so by collecting a large range of attributes that are security and privacy relevant from both devices in the labs and in the future from crowdsourcing. That could be hardware attributes, like for example, that embedded smart card support for storing encryption keys that we call Strongbox, how good the biometric sensors are. The system and operating system software, like the last available security patch level, if it actually supports multiple users, which kind of on-device encryption supports, if updates are seamless and so on. But maybe more importantly, what third-party, what pre-installed apps are added to that OEM firmware and what security and privacy problems could they bring. Another next step could be looking at network traffic. How chatty is a device? How much does it actually communicate on the network? And does it have some basic lower level network privacy like address randomization and so on and so on. We have currently 27 going towards 30 devices in a first lab in Linz. There are some devices at Google sites, and we are trying to expand this to multiple virtual sites all over the world, with currently a focus on the European market with different OEMs, but from low-end to flagship devices that are controlled through ADB, and we have some network data collection capabilities, including the layer 2 network randomization here. So if anybody is interested in writing tests, in getting new attributes on there, please reach out to Alistair or our side, and we are happy to broaden the consortium and to just take on more help when it comes to checking the security state of devices that are either in our lab or actually in the field. And the last slide is shamefully stolen from Alistair on our common presentation. I love XKCD references because what we can't answer right now is how do we actually rate those devices? Can we give them stars? Can we give them some other rating like the energy labels that we have in our electric appliances? We don't know yet. So this is ongoing research. If you have good opinions on how we should rate the security of devices, please talk to us. This is a common interest and we'd love to hear more from everybody else. Thanks for the attention so far. I know this was a lot of info in a pretty short time, but I'm very happy to discuss any of these or other aspects around Android security.
Great, thank you very much, René.